Hey, what is up? Asal here from Instaproofs, and in this video I am going to talk about integrating secant x. Now the integral of secant x arises a lot in integral calculus, especially in the chapters involving trigonometric integration, or integration using trig-sub. So I figure that knowing its derivation could come very useful. In fact, most of the steps involved in the derivation come straight from integral calculus, so it can even aid in solving problems such as partial fraction decomposition and u-sub, as you'll see. So given a function f of x equal secant x, we want to derive the integral of this function in two ways. The first way, as you'll see, is much longer and more intuitive, while the second one is shorter and convenient. But then you may ask, why even bother showing the longer derivation? Well, I'm going to show the longer first because coming from a Calc B student standpoint, the longer derivation is much more natural, meaning that the thought process behind each step is more realistic in the sense that if a Calc B student were to derive secant x, they would more than likely end up doing it the longer way first. The shorter way is just a fine-tuning of the longer method, and its logic is much less apparent. When I get to it, you'll probably end up asking, oh, who would have thought of that? So let's get to it. So we start out with the integral of secant x. From here we have a variety of options. We can use the trig identity secant squared x equals tangent squared x minus 1 and plug in radical tangent squared x minus 1 for secant x in the integral. But notice that if you do that, the only option we really have left to get somewhere is to do a u-sub and let u equal tangent squared x minus 1, where du will equal 2 times tangent x times secant squared x dx. However, there is no 2 times tangent x times secant squared dx anywhere else in the integral, and multiplying 2 tan x secant squared x over 2 tan x secant squared x won't really do much either. So from a Calc student standpoint, the only other option we really have is that secant x equal 1 over cosine x. But now, where do we go from there? Well, if you let u equal cosine x, then du will have to be negative sine x dx. But again, there is no sine x. Luckily though, unlike the previous step, we can introduce a sine x in the integral by multiplying the top and bottom by cosine x, and taking advantage of the trig identity sine squared x plus cosine squared x equals 1, and letting cosine squared x equal 1 minus sine squared x. From here it should be straightforward that if you let u equal sine x, then we are getting somewhere, because du will equal cosine x dx, and that we have in the numerator. Now we have the integral of 1 over 1 minus u squared. Noting that 1 minus u squared is of the form 1 minus a squared, where we can factor and get 1 minus a times 1 plus a, we can use partial fraction decomposition to split up this integral into two integrable terms, meaning we can split it up and get the form a over 1 plus u plus b over 1 minus u, and integrate both these terms into natural log expressions, given that a and b are constants. The logic behind the partial fraction decomposition I will leave for a future video. For now, we solve for a and b by realizing that if you take common denominators, meaning we times a over 1 plus u by 1 minus u over 1 minus u, and times b over 1 minus u by 1 plus u over 1 plus u, we can get the previous expression of du over 1 plus u times 1 minus u. And this can only be true if you have the expression a times 1 minus u plus b times 1 plus u set equal to 1. We then distribute our a's and b's. We rearrange all the terms with u next to each other and all the constants next to each other. And seeing that there is no u on the right side of the equation, we see that b minus a equals 0, while a plus b equals 1. And by using algebra 1, we get a equals 1/2 and b equals 1/2. So we have the following integral. Now we are pretty much ready to integrate. By using another u-sub and letting v equals 1 plus u, where dv equals du, and w equals 1 minus u, where dw equals negative du, integrating we get 1/2 times natural log v minus natural log w plus c. Now all that is left is plugging in our u-subs and simplifying. So starting off with the natural log rule of natural log a minus natural log b equals natural log a over b, and then plugging in our respective u-subs, we get 1/2 natural log 1 plus u over 1 minus u. And plugging in u equals sine x, we are left with the following. Now from here, we can pretty much leave the answer as this. But for the sake of simplicity, we should go even further. So now, if you multiply the expression inside the natural log by 1 plus sine x over 1 plus sine x, we get 1/2 the natural log of 1 plus sine x squared over 1 minus sine squared x. And the reason I did this is because we can simplify the denominator in the natural log by replacing it with cosine squared x due to the identity sine squared x plus cosine squared x equals 1. Now by using the property that k natural log a equals natural log a to the k, we carry the 1/2 over inside the natural log and raise the inside expression to the 1/2 power. The 1/2 power then cancels out with the 2 power, and we are left with 1 plus sine x over cosine x inside the natural log. Now by splitting up this expression into 2, we get 1 over cosine x plus sine x over cosine x. From here, it should be blatantly obvious that 1 over cosine x is secant x, while sine x over cosine x is tangent x. Therefore, we end up with the natural log of secant x plus tangent x, and this ultimately is the answer of our integral. Now wow, whoa, that was a lot of steps. Definitely a good 15 to 20 steps. Why bother ourselves with that much pain, right? Believe me, as long as it was, every step was insightful, because more than not, this long derivation is as good of a synopsis as you can get for the first couple of chapters of integral calculus. I mean, we utilize a variety of trig identities, encountering integrals that lead to natural logs, using partial fraction decomposition, and whatnot. Not to mention the fact that every integral you actually encounter involves this many 15 to 20 steps. And now that I'm going to move on to the shorter, less apparent derivation, you will really appreciate that I even went through this longer one first. So again, we start out with the integral of secant x. From here, all we do is multiply secant x by secant x plus tangent x over secant x plus tangent x. And now you are probably thinking, who would have possibly thought of that? I mean, in all my experiences of explaining the integral of secant x or any other complex trig term, I can tell you not one person came up with doing this. Maybe after 10 trials, but by then someone else might have solved to the longer derivation by now, perhaps multiple times. So my point remains, this derivation is much less natural. It is way beyond the ability of our brains to mathematically foresight. So we proceed, and we distribute secant x, and get the integral of secant squared x plus secant x tangent x over secant x plus tangent x. We let u equal secant x plus tangent x, and du equal secant x tangent x plus secant squared dx. And it just so happens that we have our u nicely fit on the bottom while du nicely fits on the top. We now have the integral of du over u. We integrate and plug in our u sub and ultimately arrive at the same answer of natural log secant x plus tangent x plus c. Now this derivation only took a solid 4 steps. My theory is that after deriving the integral of secant x the first way, some early mathematician may have thought that, secant x plus tangent x just so happens to nicely fit in the natural log, as if secant x plus tangent x was in the denominator at some point in the integral, and letting u equal secant x plus tangent x will lead to the following answer. All that was left to do is somehow introduce that secant x plus tangent x in the denominator, and that was done by multiplying secant x by secant x plus tangent x over secant x plus tangent x. I mean, it really goes to show that there is never one way to approach a problem, and that just when you think you have found the answer, that answer can still always be achieved through a simpler process. That's just the elegant beauty of math. So yeah, that should do it. Until next time, thanks for watching.